This is Ms. Henderson, and this is calorimetry reference information. So this is a really good idea to write down because this is all things that you need to know and have a solid understanding of before you start trying to do calorimetry practice problems. So what you need to know is that C stands for the specific heat capacity. So let's take just a moment to get all of the things that start with C straight. So this is little c, as in lowercase c. So lowercase c stands for specific heat capacity. It is a constant, which means that everything has its own specific heat. So the specific heat for something is always going to be the same. And then obviously, well, maybe not obviously, but there is a different specific heat for different states of matter as well. And we'll get into that in this video. So yes, specific heat capacity is a constant, but we don't represent it with K. We have a specific letter to represent our constant. So basically you can think of K as a general way to say that you have a constant. And then when we have specific constants, such as specific heat capacity is a specific constant, another specific constant that you learned in the gas laws was R. So that was the constant for the ideal gas law, and so R is always the same. So K, it's for constant in a general sense. We have a constant. And then the actual letters are going to differentiate to tell you what is your constant. So here, little c is for constant. Not to be confused with the degree symbol. That's the little circle to the top left corner of the capital C for Celsius. So degrees Celsius is something totally different. So don't put a little no little degree sign in front of specific heat capacity because it's not relative. It just is. The degree sign means something is relative. So for Celsius, we need a degree sign because Celsius is relative to water. So that's what it's saying. So specific heat capacity, little c, is different for different substances. So for example, water has a specific heat capacity, lead has a specific heat capacity, fluffy bunnies have a specific heat capacity, and the way that they find that is basically they take something called a bomb calorimeter and they put whatever they're trying to figure out in it and they burn it. And they see how much energy is released, and then from that they can calculate the specific heat. And you will do those kind of exercises. So like literally, if you took a fluffy bunny and you put it inside a bomb calorimeter and you burned it up, you could see how much energy was released, and then you could see what the specific heat capacity was of a bunny. What does specific heat capacity mean? Specific heat capacity is the amount of energy you need. Remember, energy is joules. It's the amount of energy you need to take 1 gram of something and raise it by 1 degree Celsius. And that is different if the states of matter are different, because it's going to take a different amount for if it's a solid, or if it's a liquid, or if it's a gas, because each of those 3 states of matter have different amounts of energy. Which one has the highest energy? That would be gas. So gas particles have a high energy, and then liquid have, you can think of them as kind of the medium energy, and then solids have the least energy. Do they have no energy or no movement? No, they don't. They just vibrate in place. So let's take a look here at some specific heat capacities that you're going to need to know. So we're going to look here at H2O. So this, when we say C of H2O, we really mean C of liquid water. This one is C of ice, so like when you have H2O that's solid, and then this one is C of steam or water vapor. And you notice here which one takes the most energy to increase the temperature by 1 degree C of 1 gram. Well, that would be the liquid water. And water is incredibly special. We could dedicate an entire chapter, we could actually dedicate an entire class to studying water, because water has very special and actually kind of unexpected properties, such as solid water is less dense than liquid water. That's why your ice floats in your cup, because basically anything that's less dense than another thing is going to float in that thing. So ice less dense than liquid water, so ice floats in water, which is good for the oceans and polar bears because otherwise the polar ice caps would be underwater and then no polar bears or leopard seals could go on them. So basically you're going to use these specific heat values depending on the temperature of water, and they only work for water. So if you had a different material, you would either be given that material's specific heat capacity or you would be given all other information and then have to figure out the specific heat capacity of that material. So really quick, this is the unit for specific heat capacity, and that is getting at one of the questions in the POGIL where you had to use the experimental data to calculate C. And so what you were supposed to see from that is that for C you got one big unit. So here you don't plug in any gram values and you don't plug in any Celsius values. Don't do that. This is just one unit. It's the same exact idea as the ideal gas constant R in the gas laws. So let's take a look here at when to use these. So you might not be super familiar with the Celsius temperature scale and how it is based on water, and that's why we have nice even numbers. So for example, the freezing point of water is 0 degrees Celsius. So below 0, the water would be in the solid state, and we tend to call that ice. So if it was below 0 degrees, you would use this value. Between 0 and 100, that is going to be liquid water, so you're going to use this value, and we tend to just call that water, yeah? Okay, so you're going to use this value, and I might say C of water. Sometimes I say C of H2O, because I tend to think of H2O as in the liquid form, and then I just differentiate for the other forms. Above 100 degrees Celsius, well, that's going to be in the gaseous state, and remember that the word we use for something that's in the gaseous state but is not normally in the gaseous state at room temperature is vapor, and then we are even more specific here saying that it's water vapor, and people just tend to call that steam. So you'll see this. So these three values will definitely be given on your test. So no need to try and memorize them, no need to even try and remember them. Just know, but you need to know though, this. So basically you need to know that the freezing point of water is 0 degrees, and the boiling point of water is 100 degrees Celsius. And so if you're below 0, you're going to be solid ice. If you're between 0 and 100, you're going to be liquid water. If you're above 100 degrees, you're going to be steam. So you need to know at the different temperatures what state it's in, so then you can know which one to use. So all of this only works if you don't have a phase change. So like if you go from negative 25 to 25 Celsius, you have had a phase change, so you would have to do 3 separate calculations. But if you're like going from 25 to 37 degrees Celsius, then you're fine. You can just use this, and your Q is equal to MC delta T, and that equation will actually be given to you on your test, but you might find that you remember it when you're doing all the calorimetry problems. And that is the calorimetry reference info.